Hello, and welcome back to our series on technologies of herbal concentrations. Today, we're going to be talking about how we can engineer um, our extraction processes. As a reminder, in this module, we're talking about how we can move molecules from inside the plant to an extract, and then today, we're talking about how we can maximize the extraction we want. We're going to be talking about equilibrium in single stages. We'll talk about multi-stage extraction, different types of multi-stage extraction configurations, including co-current, countercurrent, and cross-current flows. And then we'll talk about the individual extraction operations, including their key variables and how we can think about them. And lastly, we'll talk about pros and cons of these various extraction techniques. The first thing to remember are some key engineering fundamentals that are going to control our behavior. We have two pieces, so one being equilibrium, right? And this is going to control things like uh, partitioning of molecules between phases, as well as progression of reaction extents and kinetics. And these are going to control rates, so how fast things happen. And these really we can think about in terms of diffusion and reactions. The knobs that we can control in terms of these various extraction techniques are generally things like time, so how long we run a process, temperature, what temperature that pressure, what temperature that process runs at, pressure, the concentrations of various components, which solvents we're using, and particle sizes. Each of these different knobs are going to control either control equilibrium uh, or kinetics or both. And I've listed here. So time is really a kinetics effect, particle size is a kinetics effect, while temperature, pressure, concentrations, and solvents are going to affect both equilibrium and kinetics. The combination of how we construct our system in terms of the equilibrium and the kinetics will dictate our extraction effectiveness. Okay, so like I said, we have these different control knobs, but how do we exploit them, right? And so what we really are looking for are property differences that we can control or exploit in order to preferentially extract one set of molecules over another. So for example, we could have differences in volatility, right? So how readily something moves to the gas phase, its solubility, so differences between two molecules and whether they want to end up in one liquid versus the others. We can use property size, density, surface affinities, and permeabilities. And each of these different properties correspond to various unit operations that will conduct separation. So these can widely be viewed in terms of distillation, extraction, filtration, adsorption, and various membranes. I first want to think about an extractive stage. So an extractive stage is bringing two or more phases into contact, such as oil and water, and allowing equilibrium to establish between those. So maybe there's molecules in one, in the oil, and then they partition between the oil and the water. And then we draw off um, one of those phases versus the others, right? So the equilibrium will dictate uh, the effectiveness of the stage, right? So how much separation you get, while kinetics will determine how large of a piece of equipment that you need in order to reach equilibrium. Okay. So we can take an example of what one of these stages looks like. So maybe this is a distillation column, I'm going to draw this sort of an engineering diagram type style so you get used to looking at this. These diagrams, right, we showed in black boxes last time, but we can start putting symbols in there that will correspond to engineering practices. So here we have our flow in. We have this sort of square looking like thing. This is going to represent our maybe a flash stage. Don't worry about what flashing means, but we'll talk about that in a second. This flash stage generates a gas, and then at the bottom we have maybe a liquid, and then we can pull off we pull off the gas from the top, we draw the liquid from the bottom. This leads to names for these different streams. So the tops or the top stream, the bottoms or the bottom stream down here. If I'm dealing with gas phase, we generally also want to know, sorry, in general, we always want to know what the fraction of the different molecules are in our inlet, our top, and our bottom stream. And so remember, we talked about mass fractions or mole fractions or speciation fractions, and we generally write liquid fractions with an X and a subscript showing what that fraction is. And for gas phases, we generally write a Y with the subscript. This is just a view, some notation to help us easily distinguish between liquid and gas phases. Okay, so this might be a single separation stage. I have maybe a liquid or gas coming in here. I have this vessel, which is at a single temperature and pressure. We form equilibrium right through phase changes. Some of the molecules evaporate. That concentrates the remaining molecules in the liquid, and then I draw them off the top and I draw them off the bottom, right? So this is one stage of a separation process. This stage could be the only stage that occurs, or we can chain them together. So this extraction unit operation could be a single stage, or I could have multiple stages where the outputs of one stage go to the inputs of each additional stage. Right? How we run and the idea between having multiple stages is I can further concentrate each the molecules more than I can in a single stage by changing temperatures, pressures, or something else between the different stages. Merely just separating what's in the liquid phase from what's in the gas phase, right? I'm going to have to reestablish equilibrium when I move into the secondary, tertiary stage. When I have different multi-stage systems, we have various different flow patterns that exist. So the first, the most straightforward one is called co-current feed. I take, let's say I'm doing a liquid-liquid extraction. I take a feed and a solvent. I put them both into stage one. I allow it to establish equilibrium. I move that into, I take both the raffinate, so the liquids, um, the stuff that is holding behind. I have my extract. I move it to stage two. I reestablish equilibrium. I then move to stage three, and I reestablish equilibrium. This is a very ineffective method because as I move from stage one to stage two to stage three, equilibrium is going to be reestablished. And so this is effectively the same, these three stages, as if I had moved directly to stage three. Therefore, we generally operate multi-stage systems in what's called cross-current or countercurrent flows. I'm going to start with countercurrent because it's sort of the opposite of co-current, and cross-current is sort of in between. In our countercurrent flow, I have one feed that comes in from, say, the left, and another feed that comes in from the right. So this feed stream that moves this virgin feed that's moving into stage one is seeing this extraction output that comes out of stage two, right? And then stage two sees the feed that's already been exposed to that stage one solvent. So it's been partly diluted, and this uh, is exposed to the solvent that's coming out of stage three. And then, stage three gets the remnant feed from stage two and virgin solvent, right? So we have virgin solvent on the right, virgin feed on the left, and they're moving past each other. The benefit of this set is this virgin solvent has none has no of the none of the compounds that we want, right? So it's got as much extracting power, as much driving power to pull out compounds that you're ever going to get with this solvent, right? So this feed containing our desired molecules that moves from stage one to stage two to stage three, right? It should be mostly used up, right? And so the used up set, which right, has the lowest driving force to push molecules out of the feed, is exposed to the virgin solvent, which has the greatest pull of molecules that we're going to see. Same thing on the on this left-hand side, the raw feed, which has the largest oomph for pushing, is exposed to the weakest driving force from the solvent side, right? So we're maximizing this countercurrent set maximizes the extractive capabilities. We can do a cross current flow, which is sort of in between where the feed moves from one stage to the next stage. But in each of these stages, fresh solvent is added. So, right, the solvent comes down here. I end up with extract one. I have new solvent that comes through here. I have extract two. A new solvent comes in here and I get extract three. So this is going to, again, have a large concentration, but I have multiple outputs which are going to have different concentrations, right? Because there's different driving forces. So E1 is not E2, is not E3, right? So I'm going to have different sort of qualities coming out. Okay. Now that we've sort of talked about individual stages, combined stages, multi-stage systems, and different flow patterns, I want to talk about what the actual stages look like and how they operate. The first and simplest type that I want to talk about is called a flash unit. Over the course of the next few slides, we're going to be using this format. Up here, I'm going to have the name and a little description. I'll talk about the inputs and outputs, the key separation principles, the knobs that we, as the person designing or optimizing the process, can turn, the typical use case in herbal extractions. I'm going to show a depiction up in this upper right-hand corner, and then we'll talk about special charts that we can use. So a flash unit is our unit that's going to allow a gas or liquid to partially condense or vaporize. And that is going to then allow us to separate the liquid phase from the gas phase and allow us to separate the more volatile components from the less volatile components. Over here, I have this depiction, and you'll recognize this from the example that I showed a few slides ago. We have input that's going to go into this tank or vessel, which we'll call our flash unit. That flash unit is held at a certain temperature and pressure. That's going to cause this inlet fluid to partially vaporize, generating our gas and leaving some liquids behind. Those liquids can be drawn off, as can our tops. leaving hopefully different compositions in the tops and the bottoms. So in terms of input, we have one liquid or gas phase that goes in, and one gas phase that comes out, and one liquid phase that comes out. So we end up having two output streams. As has sort of been mentioned, this depends on the separation principle of differences in volatility. So if I have two molecules in there, we're counting on it that some of those molecules are more likely to show up in the gas phase than the liquid phase. Okay. So we can control different properties in this set by changing the temperatures and the pressures, right? So I can either pressurize this vessel or decompress this vessel or heat it up or cool it down, and that will change what these fractions are that move into the tops or the bottoms. Okay, and so we can see that down here in this separations chart, which I'm showing. This is a phase diagram that really dictates the behavior of our flash operator. Down at the bottom, I have the fraction of component one. So maybe this is a molecule. Let's take menthol, and then maybe the top is the mole fraction of uh, ethanol or water, right? So if I sit down here, I have the mole fraction that's on the x-axis, and on the y-axis I have temperature. So what temperature I'm operating this vessel at. I also have two black lines. These black lines, this top black line is called the dew point curve. So that's the line that distinguishes between everything being in the gas phase. And then this bottom line, everything below this bottom line is our bubble point curve. That means everything in the unit is going to be in the liquid phase, right? So moving above the bubble point, I'm going to start vaporizing. Moving below the dew point, I'm going to start condensing. What you'll notice is there's this envelope. This is the envelope that we want to operate our flash unit in. Because here, if I have some sort of input coming in, so I'm going to draw this as this green line. And if I'm operating at the temperature that's this red line right here, right, I can see this intersection. I'm going to end up with two phases, a gas phase and a liquid phase. If I go over to the liquid phase and drop down, I can see that that liquid phase has now been concentrated in component one compared to the input, right? So I've got more menthol than ethanol, right? Conversely, if I go over to the dew point curve, this will tell me what the mole fraction is in the vapor phase. We can see that in this example, if it's menthol and ethanol, we would have less menthol in my vapor phase compared to the inlet quantity. Okay, so to see how much I have a separation, I take my inlet stream, I go up to whatever temperature I'm operating at, I draw two lines, I get the vapor phase, and I get the liquid phase down here. A flash operation is usually used in a solvent recovery and concentration. So usually we've already done some sort of extraction, and I just want to remove a solvent, whether that's water or an extracting solvent. Okay. All right. So this diagram is all that you need to design your flash unit, right? So the key points I want to be working within this envelope, and then I want to pick for whatever concentrations that are coming into my unit, I want to pick some operating temperature that lives within this envelope so that we can get a difference in vapor and liquid pressures, concentrations. All right. now want to step back and do a short series about different grinding types. Sorry, mechanical processing, starting with grinding. So grinding is a unit operation that is going to reduce particle size. Here I would have some sort of hopper or distributor. I take, some uh, you know, plant materials, and then I send it through maybe some sort of ball mill or a bunch of essentially industrial sized blender or something that will crush things um, in here. So I start with one solid, right, coming out of the hopper, and I end up with a smaller, a solid that has a smaller particle size. And the key thing that we are trying to do here, we're not separating, but we're trying to enhance the surface area. Okay. So the key knobs that we can turn in designing our grinding sets are our pressures. So if I'm doing ball milling or think mortar and pestle, how hard I'm pushing on it, as well as maybe speed in terms of how fast I'm running my blender. Right, so the typical use here is to increase our surface area. Where we might think about seeing charts here would be this shown in the lower right-hand corner, before and or after grinding. I can look at the particle size. So what's my average, uh, how many, what's the volume fraction, what percentage of particles have, say, a particle size of 1 micrometer. And we'll see that ball milling, as you look at this curve, which you'll see with ball milling or any type of grinding or mechanical processing, right? I'm not going to take in a material with a single particle size and end up with a material with a single particle size. I get a distribution, right? So I can see how this distribution is going to change before and after my grinding. Because of this, we often want, because there exists this particle size distribution, even after grinding, we often want to take those ground particles and sieve them, right? So in sieving, we're going to separate our particles by size. So we take this mixture of particles that come in, and I have a sieve, which is essentially a mesh of different sized squares. Um, and the particles which are larger than the mesh can't go through, but the particles that are smaller than the mesh size move through down to the next mesh, where you can separate these out again and again. And so we can do this and we can start partitioning this, breaking this particle sizes down, right? So we could say I'm going to put in a mesh. Anything larger than 1 micrometer won't fit through. So I'm going to end up with two uh, um, streams, one with particle size less than 1 micrometer and one with particle size greater than 1 micrometer. This is usually used for some sort of grinding effectiveness. So anything that maybe is overly large will be sent back for regrinding, and anything that's of our desirable size will be processed. And then usually we end up with what are called fines. So these are particles which are really, really, really small that maybe we don't want to have in our downstream process. And those might be somehow, uh, you know, gotten rid of, right? So those fines would be a loss of our material. Somewhat similarly to sieving is filtering. So filtering is again going to be a separation of solids from, so now we're going to do filtering. So it's similar, but instead of trying to separate solids into two different sets, we're going to separate solids from a fluid. And by a fluid, I mean a liquid or a gas. So in this case, we have one stream that has both solids and a fluid, right? So it could be solids and a liquid, solids and a gas. And then coming out, I have a solid stream and a fluid stream. So you can see this, fluid. This is maybe what I would draw in an engineering diagram if I have a gas phase it comes in. There's a filter, so a mesh of some sort, and it can be very, very fine mesh. It could be, paper, um, and the solids might come out the bottom because they won't fit through the paper, and the gas will come out the top. Or it can be, something like I'm showing over here, where there's liquid that comes in. Liquid and solid come in, they're pumped in, and then the solid particles accumulate on that filter medium while the liquid or gas gets to leave through the bottom. Again, we're relying on the fact that solids are going to have a distinct size, whereas the gas and or liquid can fit through more or less all particle or all mesh sizes. Right, so the key now that we're going to tune here is our mesh size, so how fine that filter is that we're putting in here. To give you a little overview of how this happens, if I have a suspension of particles in a fluid, they come down, they interact with this filter medium. I end up with the liquid filtrate, and then I end up forming what's called a filter cake. Right? So this is the buildup of those solid particles on the filter medium. In general, we have two regions as I turn this filtering process on. Initially, it doesn't take very much pressure to push the liquid through, but in this case, after 4 seconds, I have to over the course of the first 4 seconds, we have a rise in the pressure needed to push that suspension, to push that combination of liquids and solids through the filter. Eventually, we'll get our filter cake, so that solid layer will build up, and then we have a more or less constant pressure as the liquid keeps going through. And over time, this filter cake will grow and grow and grow, and then once it's gotten to a certain size, this pressure will start going up again when it effectively is plugged. We have to change then the filter. Okay, the filtering is often used in combination with pressing. So here we have a mechanical application of a mechanical pressure on the solid or the solid liquid suspension that's going to push released liquid through a filter. Okay, so here we have one liquid or solid stream, and then again, we're going to end up with one solid stream and one liquid stream. Here we can think about two different types of presses. So one is, say, a screw press. So this is a continuous process. In this case, the filter sits as a cylinder on the outside of this set, and then the sludges, or slurry or sludge, or say oranges, whatever I'm trying to, or olives, whatever I'm pressing, get put into this screw press, and um, we have a rotating screw shown here that pushes the particles through the system and presses them against that filter. So the liquid comes out, and then the remaining solids are scraped at the end and come out here. So we end up being able to do extraction continuously. What you maybe are more familiar with is something like a filter press, where I load everything into my press. I've got a fine mesh, and then I just push down on that system. In general, rather than having just one giant filter bag surrounding the material, we generally section that off into sub units with different bags, just that the filter cake doesn't build up too thickly, because on that one edge. right? So think about this as a surface area to volume ratio. I have a thinner filter cake as I'm constructing this, so I get more of my liquid out for however hard I can push. Okay. So in addition to having our mesh size as a key knob that we can work on, we can change things like the amount of force that I'm pushing on there, so the effective weight. And then often I actually have I do an elevated temperature. Even when I'm saying I'm cold pressing, we often increase the temperature of of that press to maybe less than 100 or less than 200 degrees C in order to increase the flow rate of our liquid and help it move out of that filter. And so you might see diagrams in this case of showing oil yield as a function of pressing temperature um, in how we work. So here you would end up with, at low temperatures, you generally get the highest quality, but minimal yield. Over at high temperatures, you generally have uh, low quality and high yield, right? So this goes back to that trade-off that we've been talking about. Okay, so we can take this to an extreme where we can also think about things that are membranes as opposed to filters. So in membranes, we have it's like a filter, except the mesh size is so small that it's effectively um, zero. And we end up having no longer, or not, sorry, let me go back. It's not effectively zero. There's nothing that's able to just move through due purely to size. Here we have above the molecular scale. Here we have these membranes are generally, have pores that are on the size of the molecules themselves. And so we have these very, very thin barriers um, that are going to allow certain molecules through and not allow other molecules through. Generally, we do some sort of filtration step before we would ever go to a membrane step because we don't want any solids um, uh, in this membrane. So this case, we are no longer having solids. We have a fluid input stream, and we have fluid leaving. So right, one fluid in, two fluids out. When we have our membrane, the fluid that doesn't go through the membrane is called our retentate, and the fluid that does move through the membrane is called our permeate. It's permeated through that membrane. So the separations principle here are using differences in the diffusivities of our molecules across this membrane material. We can control this by controlling what that membrane is made out of and how it's constructed. We also can control based on how hard we push, the temperature of the system, and then how quickly things move through the system. This is often used in purification steps, concentration type steps. What you'll often see in charts detailing membranes is the flux, right? So either just J by itself or the relative flux, which is the flux of one versus the other of two different molecules as a function of temperature, right? So the greater the flux, the more you can get, and the greater um, the ratio of this flux of what you want over what you don't want, um, determines how well this is going to separate. I want to make a key note that whether you're on the retentate side or the permeate side doesn't strictly matter. The key thing is we now have one side which is enriched in one molecule and one side that's enriched in another. So maybe the retentate side has the molecules we're after, um, even though they're not the ones that have gone through the membrane. So sometimes we want the retentate side, and sometimes we want the permeate side. Okay, now we're going to move away from mechanical processes and think about a process that you probably use often, which is drying. And so this is application of heat to remove liquid, which is usually water, from a solid. So we have one input, solid, and um, a wet solid. Sorry, we have one wet solid that goes in, and then we also have a carrier stream, something that's going to carry the water or the other liquid away. So coming out, we have a dried solid stream and a gas stream that's um, has more liquid or more of the liquid molecules in it than it had to start with. This is an example of a tray-based dryer. Here you would have trays that are stacked up, um, and you would have your solid very loosely packed. So, we want as thin layer as possible. We have air that's sucked in and a fan that's going to move air through the system, and then some sort of heater to heat things up. And then we have air that wetted air that's going to leave the system. And over time, water is constantly pulled out because we have hot, dry air that goes over this wet solid. So the solid stays behind, the wet goes, the liquid molecules move into that dry air, and then they're eventually pushed out. Again, here we're using differences in volatility between that liquid and whatever the solid is. This is usually used in water reduction, water removal, and to improve storage. So maybe you collect your herbs or spices, you then dry them for both reduced weight, but then also it can help prevent a microbial growth and product degradation. Here's a chart that shows the relationship between the humidity of the air and the dry temperature down at the bottom. Over here, I'm not going to go too much into detail. There's a whole class that will talk about you, but you may come into this looking at drying. These different lines will tell you whether gas wants to vaporize or not. So we want to, in general, be below these relative humidity lines, right? So we want the air that's coming in that's moving through here to be below the saturation level of that liquid at the temperature I'm operating at. Okay, similar to drying, we have roasting. So here we're not trying to drive a removal of volatile products from the solid, but we're trying to change those products, right? I'm heating something up in order to change the underlying chemistry. So I'm putting one solid in plus heat, and I'm getting one solid out. This isn't really a separation, but it is going to change the underlying set of molecules. This is done often for coffee roasting, spice roasting, decarboxylation in the cannabis industry, right? We have sort of, here I'm showing two different types of roasters, a sort of horizontal set where I have a hot plate at the bottom, and then paddles which are going to move those solids around. I could have a rotating drum with those solids in there and as they're heated up. The key thing is we often want to keep those particles moving because one edge of that set is very hot and we can end up burning our valuable solids, right? So we want to um, tune and carefully check the temperature that I'm operating at and how long I'm holding things at temperature. So you may see charts for different types of roasters that have time on the roaster versus the temperature of the different of say the coffee beans or something else, and then we can equate that to different um, uh, styles of roast or different reaction extents of the compounds. Okay, I now want to go back to that general idea of flashing. Um, and this is gonna, that idea of flashing is going to be the key concept in this overarching set of things called distillation. So distillation is the application of heat to drive vaporization of some molecules in an input stream, which is then cooled to recover liquid. So if I look at my depiction, I have my sort of something that looks like a flash unit. I have gas or liquid that's coming in here. I allow phase separation to happen. I then have my tops. I run them through some sort of heat exchanger. This circle with the little lightning bolt is the symbol for a heat exchanger to cool that material down, and I'm left with two liquid streams. Once again, just like our flash unit, um, this has got, we're working on differences in volatility, right? And so the temperature, pressure, and throughput of this unit is going to dictate how well it operates. And this is typically used in terms of um, essential oils, whiskeys, gas refineries, etc. They're all based on distillation. I'm not going to go into this diagram because we spent a long time talking about it in the flash unit, but this is going to be the key set that will determine the performance, has all the information needed to determine the performance of distillation. And now I'm going to go in and talk a little bit about different types of distillations. So the first one is batch distillation process. So in this case, we still have a tank. We're going to heat it up, driving a formation of a vapor phase, which is then cooled to get our desired product. However, this is done in a single batch. One liquid stream enters our still, and then that still is heated. Um, and we are constantly pulling the gas off the top and recondensing, but that the bottoms are going to stay in the still. They're not continually drawn off. This has again time, how long, sorry, has temperature and pressure as key knobs that we can control, as well as how long we do our distillation. Typical uses are things like gin or essential oil extractions. Why time is really important in batch distillation is if I think about my operating envelope of our phase diagram over time, um, that point which I put in there initially is going to become more and more concentrated. So um, uh, my concentration is going to shift, right? So when I design this, I may need to change temperature, right? Change the temperature over which I'm operating with time to keep driving off the change the concentration, or I'm going to hit some sort of point which I can no longer drive the desired change. Similarly, the concentration of my vapor is going to change over time. So what molecules are coming off are not going to be consistent over time, right? As I'm moving this set, I can change my overall behavior. This is why if you were doing single batch distillation of alcohol, you have to be careful and throw out the very first set, the very first set of your tops which come out because those contain methanol, right? This is why there's all those things about moonshiners going blind because they're not throwing off the methanol. But as time goes on, the what's driven off changes. You then move on to your different phases. So if you collect your essential oils early versus medium versus late, you're going to get different notes. You're going to have things that volatilize less easily the longer you wait. Okay, we can also have fractional distillation. In this case, we're going to again uh, have an input. This is going to usually happen continuously, but this is designed in such a way that there are multiple effective stages in here. So instead of having just a single stage distillation like we sort of had in batch, we have this construct so that there's multiple effective distillations all happening at the same time. This leads to much higher concentrations in the same unit and is useful for continual production. I'm not going to go into detail, but if you are interested in any of these topics that we're discussing today, there's an entire class on separations offered through the chemical engineering program that will tell you all of these things in very intimate details. The last distillation type that I want to talk about is steam distillation. So this is really the workhorse of a lot of essential oil extraction. This is going to work somewhat like a batch distillation system. I'm going to have a single unit that everything is going to be loaded in at the beginning. And I'm going to load, there's going to be some sort of tray or mesh or separator about halfway up this unit. In the bottom, I'm going to load it with water. That water is then heated and vaporizes. That steam is then going to rise up through this holder, which is perforated as a mesh, and interact with the biomass or whatever is sitting here, right? So in this case, we're going to put herbs and spices, plant material up here. And that steam is going to be what does the heating um, of our plant matter to drive this vaporization of the essential oils. So it moves up. So after it's contented, it's heated it up. We have then both vapor, um, essential oil, and water. We condense it. And then we go into this separating unit, which is literally just going to be the oils will float to the top and the liquid water will float to the bottom. So this is our hydrosol. And this is our essential oil. We then have two choices. We can either just collect this as is, leaving us with essential oil and hydrosol, or I can then, of course, could bleed back some of that or recycle some of that water back into our distillation setup so that I'm, having less water move through this system. Sorry, so I'm having less collection of water at the end, and I can save some water. Our key knobs again are going to be temperature, pressure, and how long I'm going to run this for. It's going to be very similar to batch distillation. The difference being, of course, the separation, the physical distance between the heating element, and then using steam as a heat transfer medium, right? We're using it to transfer the heat to our plants. The key reason that we do this is because we generally don't want our expensive biomass getting scorched, right? We don't want that touching whatever medium we're using to heat, whatever mechanism we're using to heat that distillation system, right? So if I look down here at the temperature versus vapor pressure, right, I can change by changing the pressure in the system. I can change the temperature at which this, the water will boil, right? If I lower the pressure, just like going up in the mountains, if maybe I lower the pressure in that vessel down to 600 torr, I can cool my, have that system run at 95 C rather than 100 C, right? I've lowered the maximum temperature that my plants are going to be exposed to. I could also change my uh, carrier gas, that water for ethanol, say, and now the maximum temperature they'll see is 78 degrees centigrade. All right, so if I know the vaporization temperatures of the oils that I want, I can start playing around with how I'm pulling them out. All right, now we're going to talk about the other major workhorse of this process of extracting essential oils and other natural products, and that's solvent extraction. In this case, solvent-based extractions. In this case, we contact the solid, so the plant matter, with a solvent directly to dissolve the target molecules into that liquid case. So we have liquids and solids which go in, we have a liquid stream and a spent solid stream that comes out. So in general, this is going to be coupled with filtration, right? So that I can then separate the liquid from the solid. The key knobs that we turn are going to be our solvent. What solvent are we using? What temperature are we using? What are the particle sizes? How long I leave the solvent in contact with the plant matter, and then the solvent to solid ratio. I'm going to have a key diagram which looks very familiar to you from the liquid gas equilibrium. Here we can think about this where all of our compounds are sitting um, in the solid phase, and over here we have pure maybe solvent. I want to operate in this window where I have some of the molecules that are going to end up moving over into that liquid phase. This is the type of extraction technique for infusions, tinctures, oleoresins, and absolutes. We can also do a liquid-liquid extraction technique. So this is a case where I would have already done something like a liquid solid extraction, but now I'm going to contact that liquid phase that I've pulled out with a second liquid. All right, so I need two immiscible liquids, so usually an organic phase and an aqueous phase. And let's say that initially my organic compound is in water. I have these two streams that come in, I contact it with an organic phase. Those molecules want to move up into the organic phase. And so I've now separated those molecules from my aqueous phase. So two liquid streams come in, one that's got the compound I'm interested in, one that doesn't. I contact it with a second liquid phase. I get partitioning, and then because they're immiscible, right, they don't mix, I can pull off one of those phases from the other. We can do this in burettes, but we can also do this continuously. This would be, look sort of in the system where I have an organic, which is pumped in, that would come out, move up through a bunch of spacer plates. It would contact the organic phase, which is coming down. At the bottom and the top, I have settling tanks. Those settling tanks are where the liquid and the two liquids fully separate from each other. And then I pull off from the very top of my organic settling section and the very bottom of my aqueous settling section to minimize any cross-contamination of those two fluids. So each of these individual plates acts as a whole stage for this one of these separations. Again, I'm going to have a partition window where I have, how much of the phase is in the organic phase versus the aqueous phase. And I want to be working in this, range that I can control what goes into the organic or the aqueous phase. I primarily can choose what my solvents are, what my temperature is, and then how much organic or how much liquid I have. How much organic or how much aqueous phase I have. We typically use this for final purifications and concentrations um, to drive that to higher qualities or the manipulate the qualities and behaviors and distributions of molecules within our desired phase. Next is a similar idea, but here we have supercritical CO2 extraction. It's going to be like a solvent extraction, but that solvent is a supercritical CO2 or carbon dioxide. Before I go too much into this, I want to talk a little bit about what supercritical CO2 is. So I think that you're all hopefully familiar with the concepts of solids, liquids, and gases or vapors. We can show that on a phase diagram. That's what this is. That shows a temperature on the x-axis and pressure on the y-axis. And if I go to any points, I can say, okay, hey, at 100 atmospheres of pressure and negative 80 degrees C, CO2 is expected to be a solid. Whereas if I'm at 0 degrees C and 1 atmosphere, I'm going to have vaporous CO2. I can find out where it's going to act in the liquid phase. There's this point called the critical point. When I move from a vapor to a liquid phase, I condense. If I go around into this critical, supercritical phase, I'm not really a liquid and I'm not really a gas. I'm something in between. And that something in between is really interesting because for CO2, its properties, its solvating properties, the partition functions are really sensitive to temperature and pressure. So small changes in pressure or small changes in temperature can really change and tunably change the solvating properties. So again, I can take CO2. Here's an example of it transforming. I have gas in the liquid phase. I increase the temperature and pressure. I end up with this supercritical set, which is neither liquid nor gas, but has properties of both. I can, in a obviously sealed vessel, because we have to go up, as you see, to very high pressures, but not super high temperatures. And I can, pump this supercritical fluid into a vessel holding my herbs and spices. I can then very carefully choose what that solvation properties are. So I can extract what I want and partially just what I want. This is generally expensive and therefore it tends to be used for high value products. These are things like cannabis extraction, hops extraction, high-end flavors and fragrances, and decaffeination. The key control knobs are pressure, right? Because this is going to control my properties, temperature. It's going to control the solving properties, how much CO2 I'm moving through, and how little CO2 I'm moving through. The other very attractive thing about using supercritical CO2 is after I've done my extraction and the whatever molecules I'm trying to extract have ended up in that supercritical fluid, I can take this and just drop the pressure. And without going through a phase transition, that CO2 returns to a vapor phase, and I'm left with a liquid that's just the compounds that I wanted to extract. It's a very convenient mechanism of separation. However, this is a very important point. You'll notice that these pressures are very high. Because they're very high, that involves a lot of safety issues. Um, you know, poor equipment, unmaintained equipment is liable to explode due to the very high pressures in the vessels associated with doing the pressurization, the transportation of the CO2, the contacting of the CO2 with the plant matter, and then, of course, the separation of the plant matter from the CO2. Okay, so you really need to very, very, very carefully look at all of the materials that you're using in constructing of your vessels to make sure that they can easily withstand these pressures. Further, it's really important to use things like blast caps, which are pieces of equipment which are designed to fail at certain pressures. They're designed to fail at certain pressures so that if something is going to fail, you want it to fail at that point. And then those are generally connected to some sort of emergency ventilation system. Because otherwise, not only do you have an explosion, but then you have filled a room with CO2, and then you've suffocated all of your employees. We'll spend a little bit more time talking about safety in one of our later videos. Let's switch gears out of sort of the solvent extraction concepts and into more physical processes. So one of the last things that I want to talk about is adsorption. Now notice that I'm saying adsorption with a D rather than absorption with a B. So adsorption is the transfer of compounds from a fluid onto the surface of a solid. So here in my little picture, absorption, think of a sponge and fluid moving into the sponge, and adsorption is more molecules coming and sticking on the surface of a material. So in this case, we would take a liquid stream, we would pass it over an adsorbent, and the molecules would stick on the surface and not continue on with that either liquid or gaseous stream. And so we get a continual output of that fluid stream, and then we end up with a loaded adsorbent. Right? So the key principles that we're using here are the different affinities of the molecules in that fluid stream for the adsorbent. Our key knobs that we can sort of control are what that sorbent is. So whether that sorbent has different, chemical functional groups sitting on the surface to bind things, the temperature at which we're operating, the flow rate, so how fast things are moving over that surface, and then how much adsorbent we have. So this is called bed size. So if I pack a bunch of this material, how much material do I have? Adsorption is used a lot in things like color removal. So think if you end up with a bunch of green pigment in your product, you might flow it over an adsorbent to remove the green. We might want to purify things. Um, is very common. The chart that we use here is that dictates behavior is shown down here. This is called an isotherm. It's measured at a single temperature, and these lines show how much at equilibrium, how much material, how much of whatever molecule it is, sits in solution versus how much sits on the material, right? So how much is in solution and how much is on the material. Okay, so we can use this again, these diagrams to help us design, how much adsorbent we need to pull out whatever we want to pull out. This concept of adsorption is often used in what's effectively a multi-stage system called chromatography. So this is again going to be a separation based on different interactions, but this time we're going to have sort of instead of constant flow through the system, we're going to have starts and stops. So I really want to take some time and think through this. So here we have a column, a chromatography column. We fill that column with our sorbent. We have our solution that's going to be a carrying phase. So this does not contain the molecules we want. It literally just is what's going to be our mobile, we call this our mobile phase. So what's going to flow through the system? What we do is we fill our column with that mobile phase, and it starts flowing through that column. We then take whatever material that we want to separate, uh, and that's shown there in purple. And I, in a short period of time, add that on at the top of my chromatography column. I then continue to pour more of my mobile phase into the chromatography column. As that mobile phase is flowing downwards, it carries that what I'm trying to separate down with it. If there's multiple molecules, maybe you have two different forms or two different functionalized forms with a similar backbone you want to separate, they may bind differently to that stationary phase, or partition differently between the stationary phase and the mobile phase. Because of that, you end up getting this separation so that as this fluid, you can think of a line moving down as this line of fluid moves down the column, you get separation of, in this case, I'm showing this as blue and red molecules. And so you can keep adding more and more fluid and it flows down. And then you capture different aliquots of this, and you can then um, section off what you're collecting. Um, what this looks like in terms of time. So if I'm measuring time and then what's coming through, this is a detector signal, I might get the majority of molecule B coming through at time 1, A comes through at time 2, and B and C exits the column at time 3. So the knobs that we can control are what is the stationary phase, of course, what the temperature is, how much fluid is flowing through here, how long the column is, and then what the composition of that phase is. So I can, if I have water versus ethanol versus methanol versus hexane will change the partitioning um, between the mobile and the fixed phase, and therefore will change how readily things separate. Um, this phase composition can, of course, and temperature can, of course, be changed over time because this is a batch process, not continuous. I've only loaded my material in there once. So I can change over time to get things to move fast or slower. Because this is sort of a very batch-based process, this tends to be one of the more expensive separations techniques. And therefore, we generally use it again for more expensive type uh, products. So think cannabinoids, flavors, fragrances, and we use this a lot in analytical separation. We'll talk about that next time. All right. The last technique that I want to talk about is really not so much a technique, but an enhancer. So, and that's vacuum evaporation. Sometimes we want to get something to evaporate at a low temperature than it might necessarily want to evaporate um, if we were just doing heating. This is usually used, right? So in effect, we can pull a vacuum on it that lowers the pressure. It encourages our volatile molecules to leave solution and we can remove them. We start with one liquid stream. We end up with one concentrated liquid stream, liquid that's usually contained, and then some sort of vapor stream that's generally cooled for solvent recovery. The reason why we usually want to do vacuum evaporation is because there's something about the material that we're pulling vacuum on that is temperature sensitive. Okay, so that temperature sensitivity um, makes it, we don't want to heat it up. So think about this. We use this a lot in solvent removal, concentration of heat-sensitive extracts, decarboxylation of cannabinoid products. We'll pull vacuum so that they get that out without disturbing the other um, molecular composition. All right. We have now spent a lot of time covering many different types of techniques. So I just want to do a brief summary of what they are, what the property that's exploited is. Then we'll talk about some advantages and disadvantages um, of these different pieces. So we talked about grinding. This is used to create additional surface area, which is used in secondary processing steps. Um, pressing, we have a pressure, and then this is combined with filtration, which uses a size difference. Drying is used for water removal and differences in volatility of the water or whatever you're trying to dry, and some sort of um, uh, unsaturated gas phase. Roasting is used to drive chemical transformations. Distillation utilizes differences in volatility. Solvent extraction utilizes differences in solubility. Liquid-liquid extraction uses differences in partitioning between aqueous and organic phases. Adsorption utilizes differences in surface interactions. Chromatography is differential adsorption, so adsorption with including a time-based effect. Vacuums are used to exploit this volatility and sensitivities of boiling point to pressure. And supercritical CO2 is again using differences in solvation abilities and exploiting the pressure sensitivity of uh, solvation of that supercritical CO2. Of course, all of these different things have advantages and disadvantages, right? And so um, grinding leads to faster extraction due to the larger surface area, but um, it creates fines which are going to be lost. It increases the rates of oxidation due to more surface area, and it makes filtration more difficult. Pressing is great because it's simple and solvent-free, but you rarely get everything out. Drying is important for uh, storage and stability, but when you're drying, you don't just remove the water or whatever compound, you generally lose volatile compounds as well. Right, so roasting, right, you're getting new flavors, new aromas, but you may destroy molecules that you want. Distillation is great for separating volatile compounds by heating things up and volatilizing them, but that heat can damage our sensitive molecules. Similarly, steam distillation can improve upon that by lowering the temperature than compared to direct distillation, but it only works for compounds which are going to be volatile below the vapor or the boiling point of water. Solvent extraction, again, is going to can lead to high recovery and broad applicability, but it's going to require a solvent that is going to increase costs depending on what that solvent is. So liquid extraction can be a phenomenal um, purification refinement, but this requires multiple solvents, multiple stages, and then the associated losses. Supercritical CO2 has amazing tunability, and it's going to leave no solvent that could be left behind. But as I mentioned earlier, the equipment is crucial to handle safely, and this translates into higher costs. Adsorption removes unwanted colors, odors, and impurities, but it's going to remove some of your target molecules as well. Chromatography can achieve extreme high purities, but it's slow and very expensive, right? Notice that some of these two, CO2 extraction chromatography, right? High costs. They are going to be, we want to use these only for high value products. Vacuum evaporation is going to lower our temperature for solvent and it help us with solvent removal. But then again, of course, we have additional equipment that we need to buy and maintain and put in additional energy. These lead to various operations that we should think about when we're thinking about these different sets. So grinding only places where we really need faster extraction. Pressing, where we can recover essential oils. Drying is when we really care about storage and preservation. Roasting, we use when we have flavor development. Distillation, when we've got a lot of volatile compounds. Steam distillation is for those essential oils, which might be heat sensitive. If we really, really want high recovery, low heat or no heat, solvent extraction is the way to go. Liquid extraction is our one of the key places when we want to think about further purifications. And I have a good separation between liquids, aqueous and non-aqueous phases. CO2 supercritical CO2 can be very selective in fine-tuning exactly which molecules we're going to pull out. Adsorption is great for cleanup. Chromatography gets amazingly high purities, and vacuum is useful when we want a gentle solvent removal. All of these pieces come together in how we should design our extraction process. So let's just take a second and think about designing a process for handling lavender, which is moderately priced with moderately stable molecules, and how that will differ from an expensive and fragile compound like jasmine. So here, if we're thinking of lavender, we might want to do this relatively quickly. So, and do it, sorry, we may want to do this at a later date. There's no massive rush. So we might harvest massive quantities of it, dry it so that I can do many small batches instead of only one large batch. I can then take the dried material, um, grind it so that I have a high high surface area, and then run something relatively inexpensive like steam distillation. Conversely, jasmine is really expensive and its molecules are fragile. Therefore, anything that requires heat, you don't want to do. Additionally, these tend to be somewhat volatile. So we want to get these molecules into our storage form quickly. So we don't want to dry them. We generally take the jasmine flowers, we as quickly as possible can get them into a solvent to start extracting them. We then filter them to remove anything that we don't want, and then have some sort of solvent removal process. So either using a vacuum removal or some other slow process that doesn't require heat to so we don't damage our molecules. Okay, today, hopefully this is you've now got a pretty good idea of how we can design um, the movement of molecules into our extract. You understand equilibrium and single stages. You have an idea of how we can do multi-stage extractions. You have an understanding of co-current, countercurrent flow processes. We've covered a lot of unit operations and talked about their pros and cons of these techniques and started thinking about how we can put them together in a full process. All of these unit operations, there's tremendous amount of math and detail that can go into each one of them that we just don't have enough time to cover. But I highly recommend you, if you're very interested in that, going and taking our separations class, and you'll spend an entire semester looking at the detailed design of every single one of these plus additional sets. For next time, we're going to talk about how we can actually measure these concentrations and yields, and then use that to start constructing some of these plots, which we've been relying on for our design of these materials. And with that, that's going to bring an end to our fourth module, which is the engineering of herbal extractions. All right, see you next time.